There's a law in physics that has stood the test of time. Laws come and go. Sometimes we discover new things, we have to scrap them, amend them, adjust them, tweak them, throw them away. But there's one law that has been around for a long time, and no one has ever tried to damage this law or discovered any experiment that has shown it to be wrong, and it's called the law of conservation of charge. And this is electric charge is what we're talking about in this particular example. So what does this mean? Well, imagine you had a box, and inside of this box I'm going to put some charges. So let's say we have a particle here and its charge is positive 2 coulombs. And then we have another charge flying around in here, and it has a charge of negative 3 coulombs. And we have another charge over here that's got, I don't know, positive 5 coulombs. These are flying around. What the law of conservation of charge says is if this box is closed up in the sense that no charge can enter or exit. So I'm not going to let any charge come in, and I'm not going to let any charge go out. If that's the case, the total charge inside of this region of space has to be constant when you add it all up. So if you want a mathematical statement, I like math. The mathematical statement is if you add up, the sigma is the fancy letter for adding up, all the charges in a given region, as long as, here's the asterisk, as long as no charges are incoming or outgoing, then the total amount of charge in that region of space has to be a constant. This math looks complicated. It's actually easy. All I'm saying is if you add up all this charge, positive 2 coulombs plus 5 coulombs minus 3 coulombs, you'll get a number, and what that number represents is the total amount of charge in there, which is going to be 5 plus 2 is 7 minus 3 is 4. Positive 4 coulombs. You ever open up this box, you're always going to find 4 coulombs in there. Now this sounds possibly obvious. You might be like, duh, if you don't let any of these charges go in or out, of course you're going to only find 4 coulombs in there because you've just got these 3 charges. But not necessarily. Physicists know if you collide 2 particles, these things don't have to maintain their identity. I might end up with 8 particles in here at some later point in time. And if I add up all their charges, I'll still get 4. That's the key idea here. That's why this is not just a frivolous, sort of meaningless, trivial statement. This is actually saying something useful. Because if these were protons, they're not, because this is a positive 2 coulomb and the proton has a very different charge. But for the sake of argument, say this was a proton, runs into some other particle, an electron, really fast. If there's enough energy, you might not even end up with a proton and an electron. You might end up with muons or top quarks, or if this is another proton, you end up with Higgs particles or whatever. And so at some later point in time, here's why this law is important and not trivial. Because if this really is closed up, and the only stuff going on in there is due to these and whatever descendants particles they create, at some later point in time, I may end up with, like, say this one, it doesn't even have to have the same charge. Maybe this one's positive 1 coulomb, and I end up with a charge over here that has negative 7 coulombs. If these were fundamental particles, they would have charges much smaller than this, but to get the idea across, big numbers are better. And let's say this is negative 4 coulombs, and then you end up with some other particle you didn't even have there. None of these particles were there before, and some charge Q. Now we end up with these 4 different particles. I don't know, these combined, there was some weird reaction and they created these particles. What is the charge of this Q? This is a question we can answer now, and it's not even that hard. We know the charge of all the others. We know if you add up all of these, you've got to add up to the same amount of charge you had previously, because the law of conservation of charge says is if you don't let any charge in or out, the total charge in here has to stay the same. So let's just do it. What do? We add them all up. We say that positive 1 plus negative 7 coulombs plus negative 4 coulombs plus whatever charge this unknown mystery particle is. We know what that has to equal. What does it have to equal? It has to equal the total charge, because this number does not change. This was the total charge before, positive 4 coulombs. That means it has to be the total charge afterward in there. That's what law of conservation of charge says, so that has to equal positive 4. Well, Negative 7 and negative 4 is negative 11. Plus 1 is negative 10. So I get negative 10 coulombs plus, oh, you know, these Q's look like 9s. Sorry about that. This is law of conservation of charge. I might add a little tail. This isn't the law of conservation of 9s. So this is a little Q. This is a little Q, not a 9. And so plus Q equals 4. Now we know that charge has to have a charge of 14 coulombs in order to satisfy this equation. But you don't even really need a box. I mean, no one really does physics in a cardboard box. So let's say you were doing an experiment and there was some particle X, an X particle, and it had a certain amount of charge. It had, say, positive 3 coulombs. That would be enormous for a particle. But for the sake of argument, say it has positive 3 coulombs. Well, it decays. Sometimes particles decay. They literally disappear, turn into other particles. Let's say it turns into a Y particle and a Z particle. Just give them random names. And you discover that this Y particle had a charge of positive 2 coulombs. And this Z particle had a charge of negative 1 coulomb. Well, is this possible? No, this is not possible. If you discover this, something went wrong. So because this side over here, you started off with positive 3 coulombs. Over here, you've got to end up, according to the law of conservation of charge, with positive 3 coulombs, but positive 2 coulombs minus 1 coulomb, that's only 1 coulomb. You're missing 2 coulombs over here. Where'd the other 2 coulombs go? Well, there had to be some sort of mystery particle over here that you missed. Something happened. Either your detector messed up or it just didn't detect a particle that had another amount of charge. How much charge should it have? This whole side's got to add up to 3. So if you started off with 3, over here, these two together, Y and Z, are only 1 coulomb. That means the remainder, the 2 coulombs, the missing 2 coulombs has to be here. So you must have had some particle or some missed charge that has positive 2 coulombs. Is that another Y particle? Maybe. That's why physics is fun. Maybe it is now. Maybe you missed another one. Let me ask you this. So let's say we get rid of all these charges. Here's one that freaks people out sometimes. Take this. Let's say this had no charge. No charge. It was uncharged. You had some particle with 0 coulombs. Is it possible to end up with particles that have charge? Yeah, it can happen. In fact, if you have a photon that has no charge, it's possible for this photon to turn into charged particles. How is that possible? Doesn't that break the law of conservation of charge? No, but you've got to make sure that whatever charge this gets, say positive 3 coulombs, this one's going to have negative 3 coulombs so that the total amount of charge over here is 0 coulombs, just like it was before. So this is weird, but yeah, photon, beam of light, can turn into an electron, but that means it has to also turn into an anti-electron because it has to have no total charge over here. And an anti-electron has the same charge as an electron, but positive instead of negative, which is why it's called a positron. Anti-electrons are called positrons because they're the same as electrons, just positive. You don't really need to know that. In fact, you don't need to know a lot about particle physics. That's the whole point here. Just knowing conservation of charge lets you make statements about particle physics because you know the charge has to be conserved, and that's a powerful tool in analyzing these reactions in terms of what's possible and what's not possible.